hopefully not here yet. I let them know in the other classroom. And since we're recording at this point, I think we'll probably switch back. Seems like the other instructor that's in there right now doesn't really like that classroom anyway, so.
Wait, who's in there?
One of the counselors, I'm not sure what she's teaching, Mindy. But so we'll work that out. So until you see an announcement from me, they'll plan on D105 until other notice.
Yeah.
It's unlikely, but it's possible that there's a reason that we're here and they'll want to keep us here. So syllabus is gonna be pretty much the same as our plan for today. We'll talk about syllabus. And we'll talk about what the labs are gonna be. We have a little bit of leeway with labs because as you found out, they pretty much the same techniques over and over again. And we do have a fair number of distance learning type labs, not wet labs, dry labs. Already developed because back in 2020, the very first time we taught this class, was the first distance learning quarter after COVID started. So we have a fair bit in, given my background in computational chemistry. Things haven't changed too much, fingers crossed, since when I was in grad school. So we can still do might do a week or two of computational labs, but we'll try to keep it. We could easily spend an entire quarter just on computational organic chemistry and how to actually run some of these calculations.
We'll do that with the divisions.
We'll do that in the upper divisions
Yeah.
when you wind up going to a bigger school, so. So we'll do a little bit of that probably. I think grade distribution is gonna be the same as it's been. You know, labs and any homework assignments will be 30% of the grades, quizzes 30%, exams 30%, with a lab final as well.
What's the lab final for this class?
I've done it as sort of more of a journal club approach in the past where actually because after the first 2 quarters of this class, you actually have enough background that you can actually take a real OChem paper and actually dissect it in a way that everybody will be able to understand. Did either of you do the journal club with Carl's class where you presented an article?
Yes.
Yeah, it'll be pretty similar, except that I'll have more.
That's the part of the CHM223 final.
Yes, I think it, yeah.
Yeah, I mean, we spent like 30 minutes in Tiana, we spent 30 minutes both times up there. We had to go spend another lecture doing other people's presentations, we spent too much time up there.
Right. Yeah, but the trick is now that you actually have the background, everybody in the room will have the background to be able to present it at a higher level. So might be able to get a little bit more focused instead of just like a broad overview of here's photovoltaics and how they work. It'll be more
You can actually get to
an actual synthesis or an actual computational paper or something along those lines. But more on that as we get closer. Lab manual, so this is just lab manual is the one that I've written, so it's just like it'll work the same way that it has before. I might do some printouts from other sources here and there. Which interestingly enough, if you're in an educational setting, see David coming. Hey David. We're in this classroom today, so come hang a left when you come in the door. Yeah, so the lab manual is gonna be, so interestingly enough, you can actually photocopy copyrighted material as long as it's for educational purposes and it's less than 10% of the overall work. And which means since most lab manuals are like 700 pages long, you know, as long as I'm doing less than 70 pages copied from any one lab manual.
That's
I
pretty
can mix and match pretty well.
good.
So we'll supplement as needed. I was telling these guys, we might switch back to the other classroom, I'm gonna talk to the scheduling and whatnot, but until you hear otherwise, we're here.
Cool, sounds good, it's like. Just a different classroom every quarter.
Yeah, we like to mix things up.
The whole college.
This is just an example of one of the things that that we might be able to do. Looking at computational chem, but we are gonna have some different ideas for, some flexibility with labs. This is a kind of a cool one because we just finished talking about dienes, right? And how they have that S cis versus S trans are two relatively stable states. And so we can actually plot what the energy is at these different angles by basically rotating this angle here is called the dihedral angle. You can think of it as how many degrees out of the plane. If these three carbons are setting are defining a plane, the angle that this other one is rotated out of that plane is called the dihedral angle. And so we can actually calculate all these different energies using these are different computational methods. We won't get into too much of the specifics there. This is just a figure that I made when I was originally designing some of these labs. But you can actually, instead of just kind of guessing what the potential energy surface looks like, we can actually calculate the potential energy surface. And we do, and one of the things that's really interesting about this one is that the transition state is not at 90 degrees when it's exactly halfway between the S cis and the S trans. It's actually more like 100 degrees. And it could be partly because of some sterics involved there, but it could also be that you actually need to like break that S cis pi bond a little. You have to go a little past 90 to get it to be fully broken, and then it starts forming. But you'll also notice that the lowest potential energy surface isn't, or the lowest local minimum is not at 0 either. And that's definitely because of the sterics, right? These hydrogens bumping into each other causes them, even though the pi bonds are gonna get the best overlap when they're perfectly level, the sterics means that you're sitting actually more like, 30 degrees offset. And so then that actually makes this make a little bit more sense. If we're starting at 30 degrees and going to 180, then it makes sense if your transition state's kind of halfway between the two. At more like 105, 100 instead of being right at 90. So just we actually have some of the tools to be able to not only calculate these things, but actually understand what's going on now. Which is kind of fun. This is a fun quarter because we've actually put in all of the hard work. There's gonna be more hard work obviously here as well, but this is when it really starts paying off.
I think we're shy of that.
What's that?
I don't think we're shy of that.
No. There's some other, I'm also open to ideas and when you're taking your quiz this weekend and your random chemistry question, if you wanna throw out ideas for like what would be a fun lab to do. As long as it doesn't involve making substances regulated by the DEA, then I'm open to it. I know, I take fun out of everything.
There's plenty of loopholes. It's like, you don't need to really just go off what they say and say no to all those.
But yeah, multi-week synthesis. I think it's technically legal for us to do, so. If you're doing this at home, it's illegal to purify controlled substances, even if they're available over the counter. So you're like, so it's technically illegal to say extract the pseudoephedrine from Sudafed because it's a precursor and it is a regulated substance and we're not allowed to make our own more pure version. And I think technically that even applies to caffeine pills. I'm not even allowed to purify caffeine pills to get pure caffeine. But that one, caffeine is it regulated? Probably not. I think that we can probably get around that one, and I've done that lab before. And in an educational setting, so we can do stuff like that. Like there's the Nile red classic example where he, if you don't know who Nile Red is, you should definitely look. He like he makes caffeine-free Red Bull because he likes the taste of Red Bull.
The recent one was he made drinking alcohol from Elmer's glue.
Yeah,
Yeah, that's, wow.
yeah, so if you look at some of the things, like we probably won't be able to do all things, because he actually has a lot of resources to throw at these, because he's a big YouTuber making lots of money. Well,
Action Labs better.
Um,
This is garage.
Action Labs is out of his garage, but you know, if you poke around on YouTube, if you see some interesting ideas. One of the things we definitely are going to do though, one of the first couple of weeks, is we're gonna make our own Grignard reagent. And then we're gonna save it and then use it the following week to actually do a Grignard synthesis. So that one's kind of fun. But other multi-week synthesis, things like that, I'm open to ideas. The syllabus is not entirely finalized yet, so we have options.
Is there like a rough schedule that you have?
Yeah, I have a rough schedule and I'll post it. I was telling Zeke I had a sick kid all last week, and then so I actually haven't finalized the syllabus yet, and which I can make the argument pretty well that it's actually better if I finalize it after we meet, because if there's any things we need to change, that's, you know, we're open to suggestions still. But I'll have that schedule and the syllabus uploaded probably later today, if not today, then tomorrow.
How are we doing our lab today?
So today, I think we'll just do the first lab on the schedule from last time I taught this class was the carbon-13 NMR. So we actually already did that. So we're a little bit ahead of where we were last time I taught this class.
Okay.
So our lab this week will be your first homework assignment, which is just get a blank test from last quarter, blank final, and fill it out to review all the stuff, except you can do it open book and with each other and everything. So your lab will just be take the test again, open book. And actually, I might actually leave that the aromatic versus anti-aromatic section on there this time, because that's if we get to it today, that's actually the main topic we're gonna cover today. So we're only off by one lecture from being able to include that on the test. Which, although when I pulled it up to upload it to the homework file, it didn't have that question on it, so I'm not sure where what I printed came from, because it's not what actually got saved as a PDF. So, it's what happens when you have too many things going on at once. So yes, to answer your question, no official lab meeting today. Hang out in the library, work on that. I'll get some copies printed, but it's also on the Canvas sheet.
Is it the same final from?
Yeah, it's the same final from 2 weeks ago, whenever it was. So you have, and once you submit your assignment, then I'll give you your other one back. I'm not gonna give you your other one back until you do it again from scratch. So you can't just correct the things that you got wrong. Redo the things you got right too. Let's see if this link still works.
I think you're all kind of.
Yeah.
I have, today's kind of a crazy day for me, is that something I'll be able to link to it? The
Yeah,
yeah, okay.
yeah.
Well, it's you, so it's about, so.
Let me
These
see.
things are confusing, I mean.
There we go.
Too much technology. Yeah. There it is.
Right? Especially those of you who had labs in the portables, we use the aquarium pump instead of the fresh water. Basically, all he's doing though is there's coffee grounds right there. This piece of glassware is called the soft slit extractor. And basically, it'll let things steep. Solvents, heat up your solvent. A reflux, right? Basically a way to do a steam distillation. It's not more effective. The cool part is that it'll generate a siphon when it does that, and then it pulls everything else through that cheesecloth at the bottom. Watch them move into the cheesecloth when it's that top part generates the siphon. You'll see it all gets pulled down. This is just also an example. He then goes into, he tastes it and talks about how like he gets into way into like, well, it does cost this much to run my induction burner, so it's not the most economical way to make a cup of coffee, but supposedly it makes a good cup of coffee too. Obviously we wouldn't be doing that necessarily in lab, but
That's what Galen was doing in Breaking Bad.
yeah, it's same sort of analysis, exactly. But you know, in terms of if you wanted to actually look at some of these advanced OChem techniques, one of our labs we will do is a 2D NMR. Basically, you can take NMR and take a proton NMR and a carbon NMR, and you can actually put them on two different axes and see where they're connected. It allows you to do things like say, okay, well, this carbon-13 signal is associated with these protons because they show up in the right, you get the signal when you cross-reference the two signals, the two systems. So like that's, you know, one of the things that you might do for a lab report might be something like, oh, here's a new technique that they're using to do, you know, extracts. Technically, this is an extraction. Making coffee is an extraction. It's just one that everybody has some experience with for the most part. So we'll have some other cool topics like that. And if you see cool things like on YouTube or whatever, let me know. See if we can at least talk about them, if not actually do them in lab.
One of the Neil Red,
Now
Red, yeah, one of the ones that I really like that he did was make American cheese, which I didn't realize how you do that, but it's just take cheddar cheese and then you add a bunch of sodium citrate and some sodium hexametaphosphate in water, and it's just emulsifiers, and so it's just watered down cheddar cheese. I never knew that. Till like
It makes a lot of sense, actually.
Yeah.
That's why it melts so well.
Yeah, exactly.
It's got those emulsifiers in there, yeah.
Making American cheese.
That is, that actually is, that is an interesting idea. That's definitely could be one. So yeah.
It's super simple, there's
Yeah.
nothing.
Guys, and if we could actually eat, we can't eat it if we do it in
Right,
lab.
yeah.
We're using lab glassware, but if we're able to do it outside of lab. In here or in another classroom, whatever, then we could actually test that. One of the other ones that's really that I've actually seen, so coming up with new educational labs, you can actually get published in peer-reviewed journals. There's actually the Journal of Chemical Education is a premier journal for chemical educators, as you might guess. But that includes like, hey, we found a cool way that we can, or a new way we can do this lab write-up that's more effective than the other way that we used to do it. And so things like turning that into an actual lab write-up, like for other classes to follow, including the questions that go with it, that actually you can get published doing that. So there's some really cool ideas. The one that I have saved that we might do at some point is making limoncello. Because traditionally making limoncello, you take lemon peel and you soak it in Everclear and then you just filter it out and add some sugar. And then I think you add simple syrup to the Everclear to bring it down alcohol wise and to cut the bitterness. But a chemistry teacher figured out that if you do it at pressure, you can do it instead of letting it soak for 3 weeks. You can actually do it in about 30 seconds and you can actually get better results in terms of flavor. By basically putting your lemon peel in a canister and then using a syringe to force the Everclear through it. And then back the other way, you have a syringe hooked up at both sides of this canister. And you just go swish it back and forth like you're rinsing your mouth out with mouthwash.
It's like having that much pressure though.
So yeah, it's like two to 3 atmospheres of pressure, but so just what you can generate by pushing down on the syringe. But they were able to make limoncello start to finish in under 30 minutes. And then they did a taste test. So stuff like that. There's some cool stuff out there, and that actually did get published in that peer-reviewed journal article.
Is there like a big list of things that we could go through to?
Nile Red's a good place to look for. I haven't looked this year, but unless they changed it, there's not like a good way to browse those tables and contents because they're kind of all mixed in with other stuff and the titles aren't easy to parse necessarily.
Gotcha.
I'll see if I can get a list. But again, it's called the Journal of Chemical Education. And I'll see if I can post a link to a database look,
But
but
if you find something on there, you just put it inside of if it's a paywall. Is there a paywall?
there is a paywall, but I also have, because I'm an ACS member.
Oh, you have a subscription.
I have a subscription to it. I get 50 articles a year and I never use all 50. So if you see a cool article that's that's published, not just in chemical education, but it's the whole ACS is American Chemical Society. And all the biggest chemistry journals in the US all are part of their network. So unless you're talking like Science or Nature, or you're talking about something in the UK, which is Royal Academy of Chemistry or something like that, it's Royal something.
Is there a German one too?
Is there what?
A German one or a Russian one? Those ones. Right.
The German one is called Agavante Chemie. And I think there's one called Langmuir that's French. But for the most part, the biggest names are US journals.
Gotcha.
So even if you're based in the UK, you're still trying to get published in the US journals for the most part.
Yeah, that doesn't mean they don't have good ideas.
No, doesn't mean they don't have good ideas, but I don't have access to those as much either.
Gotcha.
And the more broad ones, typically. The way publishing journal articles works is the biggest name journals that have the most prestige. Typically have the most broad titles and right, they're written like if you read an article in Nature. It's written for anybody in the sciences should be able to follow along at least like a first third of the article.
Introduction.
Exactly. As you get more and more specific journals, it's harder and harder to understand what they're trying to say because they're writing for very much a niche audience. So the bigger name journals are usually the best place to look unless you're looking for that really specific niche.
I thought those niche ones are super helpful, even more so.
They can be.
People that are trying to dumb it down, because that's overcomplicate things to me.
Right, so usually with the ones that are, if you actually care about the details and the ones that are written to be broad, you have to go into the supplementary information. Cause like, if they won't even put like their procedure necessarily in the Nature article, they'll put that in the supplementary information. So if you actually are interested in replicating it, if that's your field, you actually have to go to the supplementary information to get that. So most of it's still there, they're still just as rigorous, it's just that those bigger advancements, things that appeal to a wide range, like the headline making science. Always comes from those really broad journals because they have the most impact, most people that are likely to read it and cite it. So, all that to say, be thinking about chemistry when you're browsing the internet. Always a good thing to be thinking about chemistry, right? Alright, so the review part. The review part we're gonna do in lab, or as your lab this week, and as before, the PDF is available, go to the week 1 tab on Canvas. There's a PDF available there in a place to submit it when you're done. I can get some physical copies printed. So printer's not working, and I could go to IT and get it to work, but they're gonna make me upgrade to Windows 11, and I keep like, you know, ducking out of the hallways when I see IT people coming because I don't wanna upgrade to 11. Yeah.
We can just go to the library.
Yeah.
That's the-
That's what I would be doing anyway at this point too. So that's the plan for the reviews, just to go over that test again. So we'll talk about aromatic compounds. Aromatic compounds it's a bit of a misnomer. In that it doesn't actually mean in chemistry what it means in popular language. So aromatic in popular language obviously means something that smells. As most basic, aromatic compounds in chemistry got their name because they thought that everything that smelled fell into the same category. They all had similar properties. Relatively high vapor pressures, they hit the scent receptors in the nose pretty well. So they called those compounds aromatic. It wasn't until later that they redefined aromatic to specifically mean that you have these conjugated pi systems. Because even limonene from lemon oil, if you remember limonene structure, it was a cyclohexyl group. It was conjugated, but it wasn't aromatic because you had 2 sp3 carbons on this side. Right, so there was a larger conjugated system, and this isn't the exact structure, but it was something like this. It's not fully conjugated, but it was, so it's not technically aromatic because it wasn't a real benzene ring. But most people would consider that to be aromatic because it smells really strongly.
Yeah, we're gonna be it's frustrating.
Right, because in
They're
kitchens.
like really aromatic sitting there like talking basil, it's like.
And it's because they all came originally, this was when, you know, chemistry being applied to herbs and food science. So here's some that actually are aromatic. Mystericin is one, it's in nutmeg, yes, thank you. Eugenol, we dealt with last quarter too, that was clove oil. Estragol, I'm gonna not remember that one. This one is anise. This is the flavor for fennel, like licorice flavor. Is transanethol. And then there's isoeugenol, which looks a lot like eugenol, except it's a different isomer. Basically, if you shift this pi bond over one spot, you get something that looks really similar to eugenol, but it's not eugenol. And it shows up in other compounds. It doesn't show up in cloves. But it still smells sort of like cloves. So you see that more in like something like allspice or something like that, where you get sort of like a vague spiciness, but it's not as specific as clove. And then obviously lots of pharmaceuticals have aromatic compounds. One of the reasons that they're aromatic, quote unquote, in the popular sense is because they hit their scent receptors really well. It's not just that they evaporate well, it's that they have a pleasant sort of herbally or fruity scent to them. And that's because lots of biologically active compounds also have those similar shapes, right? And so it's not a surprise that most pharmaceuticals, or a lot of pharmaceuticals, have aromatic sections to them as well, because it's just a really common biological molecule or functional group, I should say. And a lot of times something is simple. A lot of the pharmaceuticals wind up being really, really close to a biological molecule where you add one thing that wouldn't necessarily show up in biology. Not to say that chlorinated compounds don't show up in biochem, But they're pretty uncommon. For the most part, chloride is present as a loose chloride ion in biochem. So doing something like taking a regular neurotransmitter structure and then replacing a hydro OH group with a chloride is gonna let it fit into the same receptor sites, but not be the same molecule. Which can either slow down its uptake or you don't necessarily want your pharmaceuticals to bond to these active sites too well. Because if they bond irreversibly, you can't undo it and you wind up, what cyanide does basically. Cyanide bonds to the same receptor site as oxygen and hemoglobin, but it does it irreversibly. So we don't want them to bind too well. So it makes sense that we'd be seeing a lot of these similar shapes, a lot of similar aromatic compounds with a couple slight differences. Although a lot of pharmaceuticals now, the more common ones that have come out in the last 5 to 10 years are larger molecules now. They're not as small as, here's a neurotransmitter, we're just gonna change one atom. Now we're starting to look at more like multiple polypeptides, small polypeptides that are, 3 or 4 amino acids long, but one of your amino acids is chlorinated.
Like Ozempic.
Like Ozempic is a
Very,
yeah.
very large molecule. You actually look on
Yeah,
Yeah.
we looked it up together.
that. Humongous.
Yeah.
Homie's like, you should.
Yeah.
Pretty good.
Then my mom was asking about Ozempic and stuff, because her friend in UK is taking it or something.
Yeah. My mom has been on one of those new weight loss drugs. There's the Ozempic or Wegovy, or there's a couple of them that are similar.
A lot of them are like really similar to methamphetamine, but this one was the one that.
But that's the traditional approach to diagnose. Like fen was basically speed.
Yeah.
These more closely are correlated to like insulin
Yeah,
and like
yeah.
like hunger hormone.
Yeah, when I saw that, I was like, I don't know how to
Yeah.
approach this, because.
Well, if we do zoom in,
You just see the individual
So-
amino acids.
exactly, so this right here, that is a tryptophan amino acid, and it's linked to, nitrogen to a carbonyl. That's an amine linkage, which is what the biologists would call a peptide bond. So if you look, it's just a whole bunch, it's just a polypeptide, but there's a few things in here. Here's a polypeptide. Like, we don't have branched polypeptides really here. So this branched polypeptide aspect that then is tied to this long fatty acid chain is gonna allow it to interact with things a little bit differently. So this is sort of the new school way of doing it, is looking at more of these large molecule polypeptides. They're kind of slow to develop because they tend to be a little bit more slow acting. And because it's a little bit harder to tie down what are all the potential side effects. Because they're slow acting, you don't know if something's a side effect or if there's some other variable at play. So the trials for these large molecules tend to take a lot more time. Which is a good thing.
That would just decrease the chance of it being irreversible.
Right.
Attachment rate, so. I mean,
Yeah, well, just in general, there's also the side effects, especially when we start messing with hormones and neurotransmitters. So many of those systems are linked, but not in an obvious way. But like, okay, well, yes, you can treat depression by giving someone methamphetamine. That does work, but there are other side effects. It's really obvious when it's a small molecule, what the other side effects are and how quickly. These larger ones, though, things that take a couple of weeks before they start really showing effects, it's a lot harder to see what other systems are affected. Which means you have to run these trials longer. And you're looking for more subtle results. They have to be larger trial groups, because if you might only see a small, 0.5% change in something, you need a large enough trial group and control group that you can actually say that that's statistically significant. So obviously things are getting more complicated the more we understand these systems, but at its most basic, we started this talking about, look, there's aromatic stuff. So we'll come back to that. So if we're naming these, the most common aromatic we're gonna deal with is benzene, far and away. It shows up in everything, it's a common enough molecule that we're not gonna try and name it. 1,1,3,5 cyclohexatriene would be the IUPAC name for benzene, right? But we're not gonna name it that way, and so we do the same thing. We use the common name for benzene because it's be too much trouble to try and change that, so we modify benzene a lot of the time. And a lot of them are pretty easy. Chlorobenzene, nitrobenzene, ethylbenzene, bromobenzene, etc., right? However, there's a number of these monosubstituted benzenes that actually have common names. And I'm gonna test you on these. This list. Yeah, probably at least on the quiz over the weekend. In open book style, but for the most part, if you see a monosubstituted benzene, you should be thinking there's probably a common name for it. The ones that show up all the time are toluene and phenol, and then aniline and benzoic acid.
Yes, it's trying.
It's trying, right?
It's trying to follow, but
Except it's technically irregular because it's not the benzene that is part of the. We would actually name it. IUPAC name would be something like phenylformic acid or something like that, right? But it's close, right? And same with benzaldehyde. Styrene. In the UK, they actually call the polymer made from styrene polystyrene. We don't call it that. We call it by its copyrighted name. Does anybody know what it is? Styrofoam. Polystyrene. When you make that polymer and you cast it under the right pressure conditions, you get styrofoam. You have to get it to foam up by changing the pressure and letting it evaporate, letting the solvent evaporate in the right way to get it to puff up like that. And then does anybody know where you see benzaldehyde? Anybody remember mentioned it before? It's really close to eugenol.
Benzaldehyde is kind of more or less like an almondy.
It is. It's almond extract. Synthetic almond flavoring is just straight benzaldehyde. And even most almond extract you get is just 90% benzaldehyde with a little bit of there's a little bit of that similar to vanilla we talked about before, right?
Yeah.
Where you get some other flavors if you do like the natural vanilla extract, but then if you get the cheap stuff, it's just straight vanilla. Same with benzaldehyde being is almond extract. But toluene shows up a lot as a solvent. Again, hardware store solvent. So paint thinner, a lot of paint thinners are toluene based. And phenol, we talked about how acidic it is. Phenol winds up being a pretty important molecule. We use it probably used it in the ambulance, I would wager, as a topical antiseptic. No, just iodine or alcohol if you're trying to swab someone.
we had alcohol, we had povidone iodine, we had chlorhexidine.
Chlorhexidine.
Sepsis patients who are like very high risk.
Yeah, okay. So phenol you do see definitely in medical settings, maybe more in as an antiseptic, because a lot of these do have some antimicrobial properties as well. Aniline's a really common one. It is fairly nasty. It's a pretty good base. So we do see that as well. And then acetophenone and anisole both actually are not really toxic. They show up in small amounts in a lot of different essential oils. If we have di-substituted benzenes. Typically, what you're gonna do is you're gonna name it as a. Name it as a common name and then add a prefix to modify. Right, so if you can recognize that this is anisole. Then you just say, okay, nitroanisole. Right, so if you, and sometimes there's more than one common name. So pick the one that's most convenient. You know, if I had. Well, one. We had a molecule that is, where you could say the common name is anisole or the common name is toluene. We could either name it methoxytoluene or we could name it as methylanisole, be equally as correct. Although my guess is a lot of these disubstitute benzenes also have common names. And I'm definitely not gonna make you memorize all of those.
That was a good question, like, why don't they just keep the complicated thing up?
They. This one in particular, I think, is. Let's see. Oh, 2-methylanisole. The monomethoxybenzene. Is O-cresol, in which the nolic hydroxy. Oh, so if it's a. That's a common name. That's O-cresol. Well, as a human xenobiotic metabolite. Which. I don't actually know the specifics of what that means, but my guess is that that is either part of gut biome. Or it's xenobiotic, xeno means foreign. So it's
Probably
basically,
just because toluene's like foreign to human.
yeah, and so it could be the way that your body breaks down toluene is to put an OH on it and make it more soluble in water and then put it through the urinary system. But not sure. So some of these are gonna have common names, sometimes it's just gonna be a modifying existing common name. If we are trying to specify where things are, we can use the numbering system, like we just saw in Molview, where it said this was 2-methyl cresol, or sorry, 2-methylanisole. The other thing they use is rather than using, when we start talking about electrophilic substitutions, it's position, it's a substituent's position relative to another substituent winds up being really important. And in that case, we don't necessarily say just use the number, because if this is our primary carbon, we call that carbon 1 because that's the one that makes an anisole. This could be carbon 2, which would make this carbon 5. No, sorry, this would be carbon 6. Yeah. 2 and 6 are the same distance from carbon 1, right? And it's identical until we put that methyl group there, it's identical which direction you're counting. And so we kind of rate both of these, carbons 2 and carbon 6. We refer to both of those as being in the ortho position. Good question.
I guess.
These ones are called meta, which makes a little bit more sense because meta means self-referencing, right? One step removed. So they're one step further removed from being directly adjacent. Or I would hesitate to say orthogonal because orthogonal usually means not interacting.
It means parallel.
Parallel or no, perpendicular,
Yeah,
linear algebra. So
Maybe not, yeah.
Well, when we think about it, because when we remember talking about how these charges resonate around, how you couldn't put a charge directly on the one right next to it, it would jump. So it actually might be from orthogonal because you can't resonate a charge directly onto the ortho positions. But I'm not sure about that.
Yeah.
Meta makes a little bit more sense. I don't know where para comes from. Para just means the opposite. And that actually para versus parallel and ortho versus orthogonal, those are kind of opposites. But when we look at these resonating charges, we wind up with these positions having a lot of similarities. Ortho and para wind up going through substitutions at the same rate. Or similar rates. And so just so you don't have to, the numbering always works too, but when we're talking about, just like when we talk about alpha carbons and things like that, having this language to be able to talk about both of these simultaneously is helpful. All right, let's take a break. 10:50, go see if that food line has died out, get some free food over there. First week of class. Awesome. Go take a look, and then we'll come back and we'll talk about aromaticity and defining that.
Yeah,
We'll be right back.
Like the thing that we're renting was set up as like very much like a summer cabin. And the landlords just didn't wanna get rid of all the old furniture, they don't want it, but it was like, it's also massive, they were like, didn't wanna bother getting rid of it, so they're just like, you can get rid of it if you guys want. So I disassembled the bed, threw it all in the garage for now, so I'm sleeping on the floor right now. But I ordered a little like mattress, like a Japanese one.
Is this down in
It's been
Top
Framing Trail.
If it's one of the
Well,
lab,
or my book.
as long as it's one of the days where it's a lab meeting, like a project.
Yeah.
Meeting, then
Yeah.
that's all fair game because it's not.
It's on the book.
Yeah, that's kind of what I was,
That
what I wanted to
frame.
determine.
No mattress. No random.
Alright, well, I'll check in with you tomorrow.
Yeah, let me know, like, I have some.
When I found a good.
I was just gonna pull one of my
Or
old
pick up
documents and
today.
just be like, this is how, this is the data, you know, let's start thinking.
Yeah, exactly. Yeah.
You want this?
Oh, cause I only have like 10 by 12 room, it's small. There's a cow king bed, but I just got rid of. Literally.
Open up the door and you gotta jump onto the bed.
No,
That's
no.
why I was thinking just like an hour long talk, and also like showing people like, hey, I wanna make
Then
do
you
this.
have demonstrated these guys quite a bit too, probably seeing what's fun.
You know,
Yeah.
I got something slightly wider than a twin, it's not quite a full.
So
The
that's
Japanese bed sizes are weird. It was like 48 inches wide. Another 39 for a twinner.
It's measured in inches. From Japan, it's measured in inches.
Yeah, 200 centimeters long, 90 centimeters wide.
Yeah, people think that. Or.
2 meters, that's so I can advertise, that is so funny.
Person 17 years ago asked this question.
It's more comfortable.
That's exactly what I want.
Any other differences than back then?
No idea,
That's.
I ordered it yesterday, so. I got my bench, so hard, I'm just sitting on
yeah,
my.
I see it
Pull
so.
out, pushing on the floor.
Oh,
Which is good, and then I'm super uncomfortable, so I'm trying to get certified, that's great. I'll be like, this is nice.
Sleep in the back of my truck.
Just like.
For me,
Oh, yeah. Some sleep, not really.
Yeah.
It really wasn't even a sleeping pad, it was a mattress I bought.
Oh.
We're on break right now. It's a pretty comfortable classroom. It just has the smart board. It doesn't have a projector.
Yeah.
So depending on how much you use the projector.
I'll use it every class, so I just log in.
So I just log in, this just runs Windows behind this. So, you know, when you're looking things up or whatever, and I actually screen capture it, it's recorded too. So it works pretty well. That other classroom works all right for that as well, but just, you know, this is about all you have for the technology. It's right.
Get up and talk, discuss things, and that room is so hot, which they're almost 30 students, I was like, wow. Yeah, so I'll maybe I'll email Ricky and see.
That
if
would
he
be
is.
great, that would be great, I'm
She
sure.
can switch, What time does this last?
But split it in thousands.
Okay.
Or 11:50.
Okay,
Yes, I'm not trying
Thank
to go
you.
higher than like 1,000.
1,020 utilities.
Alright,
That was this one.
It's like a few miles away. It's a good bike ride, but I mean, it's fine. It's like, what can we do there?
alright, let's talk a little bit about aromaticity. Like I said, naming these things is pretty straightforward, like we were just discussing. Why it's not. Flag. You know, these are the common names that you really want to know. The only dye substituted that I have memorized is xylene. Or, yeah, xylene, because it's basically toluene with another methyl group. And again, gets used in a lot of paint thinners. Although it gets called xylol, which is, I really don't like because it doesn't have an OH in it anywhere. But if you see xylenes plural, it's usually a mixture of orthoxylene, paraxylene, metaxylene. And you sometimes see that mixture labeled as xylol especially in hardware stores, but it's the same thing, that XY, and I believe it's because it originally they used to make it breaking down some component of wood. So it's the same root as like xylem. I think that XY prefix, I believe, means it comes from a tree originally. I could be wrong on that. But so in terms of why aromatics are their own class of molecules, it actually comes all the way back to when they were first trying to figure out the structure for benzene. They knew the formula for benzene was C6H6, which, so they're like, okay, well, that means it's highly unsaturated. There should be a bunch of alkene bonds in there. We should be able to hydrogenate it. We should be able to go through all these addition reactions. But what they found is that benzene wouldn't do that. And they couldn't really figure out why until August Capulli had that idea of that he ripped off from ancient mythology of the serpent eating its own tail. The idea of resonance and these pi bonds resonating in more of a circle rather than being fixed in one place. They didn't understand why that made such a big difference. But what they actually saw, so we can actually run these experiments. You can hydrogenate cyclohexene. It's 120 kilojoules per mole that we give off when we do that. We hydrogenate the conjugated diene, and we get 232 kilojoules per mole. So not quite double because we have some conjugation there, right? If we did it with the isolated dienes, so that'd be 1,4 cyclohexadiene, we would actually get almost exactly double. So we would expect if we hydrogenate this, we should get something close to 360, because there's 3 pi bonds we can hydrogenate. But what we actually get is 208 kilojoules per mole. So that's a pretty large difference. We get 152 kilojoules per mole extra stability by having these conjugated ring structure. And that's why benzene wasn't going through all the same reactions that they would expect it to. There's something else going on. And it is resonance, but even more than resonance, there's some specifics about the way that the bonding orbitals work that allow it to get that extra stability. And that means that benzene won't go through the same reactions that other alkenes do. Pretty much, and we can force it to be hydrogenated, but like we talked about before, it's like 100 atmospheres of hydrogen at 400 Celsius in order to get this to react with a catalyst. So obviously a lot different in terms of reactivity. And we can explain that with molecular orbitals. So when we think back to talking about those conjugated dienes, those conjugated polyenes is the more general way to look at it. Having those conjugated triene, but in the ring structure allows us to mix the orbitals together in a slightly different way. So your most stable orbital is going to be, looks like two hamburger buns. Right, or looks like a donut above and a donut below, if we tighten it up a little bit. But then there's also two that kind of look like these hot dog buns, except you're adding that middle node right in the middle, but then there's two ways you can do that are equally favorable, right, because of the symmetry. Which means these two bonding orbitals are both a lot more stable than what we normally, so we don't get that nice linear stretch out your pi bonds in a line and then add your nodes in the middle and then add your nodes in thirds. The nature of it being in a ring structure allows us to do that a little bit differently and get things to be even more stable. We wind up with a larger gap between the bonding orbitals and the anti-bonding orbitals, between the HOMO and LUMO. Right, and so, you can keep adding nodes, and you'll notice that the way that they're rotationally symmetric in these. That cyclic part of it is what separates this from just being straight diene triene. What makes it aromatic is that ring structure. If you don't have that ring structure, it's not aromatic, even if it's conjugated. Right, so going back to that limonene example. Again, it wasn't exactly this molecule, but it doesn't matter. Still 3 pi bonds conjugated, right? However, and it's still a ring structure, but the pi bonds in the ring structure aren't in the same space, so you don't get these same types of orbitals formed. Right, and so what we see though is that not every conjugated cyclic system is aromatic. Because just like with the, how with the HOMO and the LUMO, as we added more pi bonds with conjugated polyenes, we saw that the HOMO and the LUMO had different numbers of nodes. Then they had that like 3 switches versus 2 switches. Changed depending on how many pi bonds were conjugated, right? We'll see the same thing here. If we have cyclobutadiene, so 2 conjugated pi bonds, still a conjugated cyclic system, but the fact that it's an even number of pi bonds conjugated means that we actually don't get the same structure of orbitals. We don't wind up with them going the same way. What we actually wind up with, the fact that it's an even number means we actually get some unpaired non-bonding electrons when we actually look at these molecular orbitals. And we know unpaired electrons are unstable, right? So this is an example of what's called anti-aromatic. So instead of getting extra stability by having these conjugated pi systems, if it's an even number of electron pairs, we actually get less stable, even though they're conjugated. Conjugation almost always means more stable, but if something is anti-aromatic, it actually gets less stable. So for something to be, we'll talk about the criteria here in a second. But here's just another example. If we extend that, so cyclobutadiene, we wouldn't expect that to be that stable anyway because it's really strained, right? But if we do the same thing with 8 carbons, conjugated ring structure. However, the fact that it's an even number of pi bonds causes this to have these non-bonding molecular orbitals, and it means that we wind up putting in getting these unpaired electrons in those non-bonding orbitals. So they're not considered anti-bonding orbitals because they're basically they're right at the line in terms of stability, in terms of energy, where things go from being bonding to anti-bonding or occupied to unoccupied. So they are technically, they are occupied orbitals, but they're the highest energy occupied orbitals. And the fact that we run out of electrons as we're putting electrons in there gives us this non-bonding characteristic. It's not technically anti-bonding. And originally the definition of bonding versus anti-bonding molecular orbitals comes from, in a bonding orbital, you have more orbital overlap than you have nodes. So basically, more bonds than nodes. In anti-bonding orbital, you have more nodes than bonds. That's what makes them higher energy, right? If you have more nodes than bonds, then you have a net force to break these things apart. And so a non-bonding orbital is basically when you have the same number of nodes as bonds. Right, so all of that to say that the whole, if we wind up with an even number of electrons or an even number of electron pairs, we get these non-bonding orbitals forming. We only see those with even number of electrons. And basically the way we can anticipate this, or the way we can explain it, is if you take whatever the if you have a conjugated pi system in a ring, if you take that structure and you put it, sort of balance it on one point. 1, 2, 3, 4, 5, 6, 7, 8. That's an octagon. Especially if I actually slid these out a little bit more, you'd be able to see it a little bit more. It's an octagon balanced on one of its points. This one's a square balanced on one of its points. If you take a hexagon and balance it on one of its points, you don't get anything that's right at this non-bonding level. You don't get anything that's exactly halfway between the two. So you don't get the non-bonding orbit. So if we were looking at the energy for benzene, we get something like this, where this is your energy level, where you get the non-bonding. There are no orbitals right there. And when we're adding 6 electrons in here, we wind up filling all of the orbitals perfectly, and there are bonding orbitals. Nothing partially filled, and nothing right at that line or above that line filled. Right, and so that's actually why this is drawn with these orbitals being in that hexagon shape. This is also that same shape balanced on one point, right? So the fact that if you have an even number of pi bonds, you're always going to get some orbitals right at that level, and they're always going to be partially filled. Right, so this is what's called Huckel's rule. I think I've mentioned my old professor who taught physical organic chemistry when I was in grad school. Who was from Poland, and he felt very, very strongly about pronouncing Eastern European names properly. He told us if we ever said Max Planck, he would fail us, so we had to pronounce Max Planck properly. Huckel was another one. It's not Huckel's rule, it's Huckel's rule. And Huckel's rule is the definition of aromatic. In order for it to be aromatic, your conjugated pi system must be cyclic, and there must be 4n plus 2 pi electrons, which is another way of saying an odd number of electron pairs. Right, and so that allows us to extend this to much larger systems. the other thing to keep in mind is this doesn't just apply to pi bonds, it says pi electrons, which means conjugated lone pairs that can resonate count. So think back to that
So give me a
thiophene.
file.
Exactly, we did the hydrogenated version of this molecule here, right?
Still resonate.
That sulfur has two lone pairs, one of which can resonate with these two pi bonds, which gives us an odd number of electron pairs. So this is aromatic, even though it's only a 5-sided ring, and it's only two pi bonds. It's two pi bonds with a lone pair. Total for 3 pairs of electrons in this conjugation. So this one's aromatic. If you get an even number of electron pairs, that's anti-aromatic. And if you have anything that breaks up the conjugation, whether that's either structurally, like shape-wise, if it's not planar, they can't be conjugated, or if you have an sp3 carbon somewhere in there, then it's not conjugated. That's non-aromatic. Those are really, if we're talking about classifying things in terms of aromaticity, you got aromatic, non-aromatic, and anti-aromatic. And so for these, no electron lone pairs in there. It is cyclic. So 1, 2, 3, 4, 5, 6. So anti-aromatic. 1, 2, 3, 4, 5, 6, 7. Aromatic. One, 2, 3, 4, 5, 6, 7, 8. Anti. And these ones I'll actually be. They actually won't be anti-aromatic when you get to these larger ring structures like this, because anti-aromatic is actually less stable than non-aromatic. So they'll actually break up their conjugation just by, if it's big enough molecule, they'll just break up the conjugation by not being planar. And so what you'll see is with these larger groups that might be anti-aromatic, you can either call them anti or non. Because if we forced it to be planar, it would be anti-aromatic. But this is a 3-dimensional molecule, so if you can say, okay, if it's planar, it's anti-aromatic, or if you just take this section and fold it over, now it's non-aromatic, that's actually going to be more stable. And with these large ring systems, that's pretty easy to do. They have a lot of degrees of freedom where they can just sort of not be planar. So anti-aromatic it's an uncommon term that you haven't really heard before, because really almost everything that's anti-aromatic can tweak its structure to be non-aromatic instead. So on the test where it said label everything, it's either aromatic, anti, or non-aromatic. I'm actually not that picky between anti-aromatic versus non-aromatic, as long as it's a large enough structure, as long as you understand that.
Whereas like the aromatic 1-7 would like to be planar.
Yeah, this one will be planar because that allows it to become more stable. Even though sterically there's some, being planar means there's some steric issues. And it might not stay like this forever. Because if it can rearrange itself to be in hexagons that are also conjugated, it'll do a little electrocyclization or sigmatropic rearrangement in order to maybe at the expense of one of these pi bonds, maybe we could get something like this where we get a smaller system, but it's in hexagons. It would probably go through some rearrangements, but even without that, that's still aromatic because it's got an odd number of electrons, odd number of electron pairs.
What about like a benzene with like another benzene attached directly to it with 2 carbons? If you know that's not really a perfect description, but you know exactly what I'm talking about.
What is the?
Yeah, one of those.
Used that before.
We did, naphthalene. Naphthalene is aromatic
It's 10.
because it's 10 pi electrons. It's an odd number of electron pairs. It's just two fused rings, but it's still one ring structure. And when you look at it, like, okay, well, that's a benzene ring, that doesn't look like a benzene ring, there's only two pi bonds there, but those pi bonds are part of this larger pi system because they're conjugated. And there's no sp3 carbons in the way. And you can extend that indefinitely. That's anthracene? No, anthracene is coal. There's a name for that I'm blanking on right now. And so on. In fact, you have to be careful how you do that so that you don't wind up drawing a carbon with 5 bonds like I just did. But basically you can extend this indefinitely in 2 dimensions. And if you extend it almost infinitely in 2 dimensions, we actually have a name for that too. Graphene. So graphene is basically a sheet of benzenes that are all fused together like this, where everything is conjugated with everything else. Anybody know what the unique properties of graphene are?
If you dope it, it's a really good conductor.
It's
really strong.
It's a decent conductor as it is. You don't even have to dope it. Doping is the process of semiconductors where you add something with either extra electrons or fewer electrons to a crystal structure in order to tweak those energy levels. Graphene is actually a pretty good conductor as it is. If you've ever done a physics lab where you make circuits, you can actually draw circuits with pencil.
I remember doing that with Kathy. We literally it was I think it was some sort of like special paper, but you just drew it out with your pencil and it worked.
Right.
The voltage carried through.
Because basically what you're doing is when you're writing with graphite in your pencil, you're just putting layers of graphene down, which means you create this really, really large conjugated pi system that allows you to resonate an electron from this side to that side. Yeah.
Jump your car.
You can short a battery. If you take a piece of pencil lead and put it between the two terminals of a 9-volt battery, you can actually short the 9-volt battery. Start a fire.
More about fixing things.
So 9-volt batteries and actually steel wool works even better. It's a really good way to start a fire in a campsite. It works better than matches sometimes. Basically take some steel wool and a 9-volt battery and you just touch the battery to the steel wool that you put underneath your fire energy though. Works pretty well that way.
Even jumper cables.
Jumper cables.
Yeah, I guess.
Actually, if you actually are going camping and trying to build fires, the best thing that I've found is actually dryer lint.
Yeah.
Dryer lint makes
Really?
a fantastic
Yeah.
kindling
That's
or a
stuff
tinder.
Toilet paper roll.
Yeah, stuff it in a toilet paper roll or in a paper towel roll, and you've got yourself a nice little artificial log that burns really, really well.
If you take it, you conceal it from the outside environment, heat it, and you got retard and burns even better to start a fire.
Oh, I hadn't thought about that. Yeah, you probably could polymerize it. Put it in a Ziploc bag and boil it or something.
Yeah, or just a tin or something.
Yeah, interesting.
And then off the record, if you put styrofoam into gasoline.
That is, and actually the so when I was in undergrad, we were in San Diego, it's a big Navy town. And one of my advisors or one of the professors, his day job was working for the Navy. And he said that if you actually go look at the old napalm tanks, they actually have they're like propane tanks. If you look at the old napalm tanks, you can actually see where some of the rivets had been going and it would grow a strand of styrofoam directly after where one of the rivets failed, because the gasoline would evaporate and you would just get styrofoam left over. And so it would basically had these little tendrils of styrofoam growing out of these tanks. That's how you knew that was a napalm tank. Also does work well for starting campfires.
Well,
Just be very careful. It'll dissolve almost anything you put it in. is the trick. Because gasoline dissolves most plastics pretty well. But if you put it in something, so don't put it in like a peanut butter jar or something like that.
I'm gonna bet.
But, and that's not technically illegal, so I don't even think we need the plausible deniability, just don't light stuff on fire. We all know that's bad.
Birch forest can also great for it's the birch bark. But then there's also this mushroom called the birch polypore, Fomes fomentarius, which grows on the sides of trees, and then you can hollow it out, like kind of cut a thing off, hollow it out, you can put a coal in there. And then I'll cap it back off, and it'll hold the fire for like over 24 hours.
See, that is how hunter-gatherer tribes were able to move fire, they didn't restart the fire every time they moved, they carried the coals with them.
Yeah, just put it in your fire.
I think, is it The Road by Cormac McCarthy, they the language carrying the fire. But that actually was an old thing from prehistoric times. They would literally carry the fire from place to place, and the person who was in charge of carrying the fire was a very important societal role. Yeah.
Don't mess up.
Alright, so let's do some more practice with these. Looking at aromatic, non-aromatic, or anti-aromatic. So. Just to go back, conjugated pi system must be cyclic. And must be an odd number of pi electron pairs. So it's A. Move those markers away, or else I'm gonna write right on the board here. For A, is that gonna be aromatic, non, or anti?
That's gonna be anti, because it has the lone pairs.
Right, it has the lone pairs, only one of which
Only one is.
can resonate, right? So it means, that means would give us 4 pairs of electrons. So either anti or non, because all you have to do is not resonate one of those lone pairs. Those lone pairs resonate when it's advantageous, when it becomes more stable by resonating, right? So they actually would just not resonate, and then you don't have a conjugated pi system in a ring. So non or anti, again, I wouldn't be picky. For either of those. B is the same way, right? And if we actually calculated these structures, if we actually looked at the most stable electron configurations and geometries, we'll actually see these two will not behave sp2, they will actually be sp3 shape, they'll be tetrahedral geometry to avoid that anti-aromatic part. See, aromatic
Is technically
because you've got one lone pair can resonate there. The nitrogen has a lone pair, but it's not going to resonate, right? Because it already has a pi bond. It's part of the pi structure. So 1, 2, 3. So that one would be aromatic as well. And these anytime you've got a ring structure where one of the components of your ring is not a carbon, we call those heterocycles. So a cyclic structure, hetero means different, right? So anytime you have one atom that's not the same as the others, that's a heterocycle. And actually, they're actually an entire field of study or upper division class in a lot of they use the term more commonly in the UK, but heterocycle chemistry is its own organic chemistry class because they behave a little bit differently.
Is it hetero?
Heterocycle.
One of these.
We've got 3 conjugated pi bonds here. Are we gonna have any lone pairs involved?
Well, no, because nitrogen's already involved.
Exactly. So aromatic, non, or anti?
Aromatic.
Aromatic. Protonate that nitrogen. Was that lone pair part of the resonance to begin with? It was same argument as up here, right?
Yeah.
Up here, that lone pair didn't participate in the resonance because the nitrogen already had a pi bond. So we can protonate it and that doesn't change our resonance at all.
Yeah.
We can't really protonate this sulfur very well. Actually, sulfur's bad as in. This one's a good example. If we deprotonate this nitrogen. That's aromatic, right? When you protonate it, that pi bond or that lone pair can no longer be part of the pi system. So we actually break up the aromaticity by protonating that lone pair. So this one's actually not a very good base. Most nitrogens are good bases because they have that lone pair you can protonate. Not if that lone pair is what's making it aromatic. That's not an issue for E though. Because that lone pair was just sitting there anyway. So this is pyridine, I believe, the protonated form of pyridine. It is a really good base because you get a nitrogen with a lone pair and protonating it doesn't change anything else. So it's a non-polar or very close to non-polar, relatively strong base. Those are actually kind of uncommon. Most of our stronger bases are pretty polar. So pyridine actually gets used a lot as a solvent in organic chemistry because it can act as a base, but also dissolve non-polar compounds. How about G?
It would be aromatic, it's still
It still has one of those lone pairs. So the difference between nitrogen and oxygen is oxygen has two lone pairs when it's neutral instead of one. So furan is the deprotonated form here. Furan is aromatic and so is the protonated version of furan. Then H looks really wonky, doesn't look particularly stable, right?
But I guess you could technically call it aromatic.
Technically, it's aromatic. Odd number of electron pairs in the conjugated cyclic system. It meets all the criteria, even though it looks weird.
That looks stupid.
It does. So almost certainly that's gonna rearrange itself pretty quickly to be some, but it'll be longer lived than you would think because of the aromaticity. All right. That's the big topic for today.
We're all expecting more.
Yeah. I think what I've done in the past is when we had a lab going in the afternoon, we actually would go through the test in class. So this was just a little bit shorter of a lecture. So that I can turn you loose on working on your review assignment. So before we end this, does anybody remember anything about the test? Again, I'm not going to give you back your test, but was there any questions you can think of? I'll pull up the blank version of the test.
We did ask about the lab.
Yeah,
I found something that, I don't remember exactly how it works, but mine will be arranged in something that's. In oxidants.
okay.
Because what I read was that it gets you a ketone from an epoxide, but I couldn't find anything to justify it.
Yeah, I think you shouldn't have needed to, there are ways to do that, but that is gonna be a rearrangement, because you need to move a hydrogen over from one of the carbons, you have to have hydrogen to move.
So it's called mind mold rearrangement. just couldn't find anything.
We'll talk about carbonyls,
Okay.
and that's probably our number one topic for this quarter, is gonna be carbonyls. And their alpha carbons and how everything rearranges and stuff like that,
Yeah.
like enol ketone.
That way, I
Um,
was trying to go a different route with the epoxides, I'm sure you saw my note, I could have done
Yeah.
epoxides, but I just couldn't figure it out because there were no good papers. At least that I had access to.
It's the 2024_exam.2 PDF for the assignment.
the one that's linked there, if it's opening for you.
Yeah.
Yeah, this is the one that I thought I asked, so it had more of the classifying. And didn't have the, is it anti-aromatic versus aromatic, since we hadn't covered that. So just do this one. Instead. Was there anything in particular?
I think it was the one mechanism, the bromine one. Not the green one.
Yeah, good.
Actually,
That one was. Did we do that?
no, that one wasn't on your list. So I changed that one out, actually.
The Williams.
The Williamson ether synthesis, so this was just gonna be a deprotonate. Yeah, the hydride acts as a base to deprotonate the alcohol here, and then that makes it a good nucleophile
And then
to attack the ethyl ketone. I think we had, and I think it was it wasn't
it was the
green or,
aluminum hydride.
it was aluminum hydride, but again, it's the same mechanism. It's just a hydride acting as a nucleophile for your reduction instead
not
of
adding-
methyl group. But it'll work the same way, your methyl group brings a pair of electrons over, just like the hydride would.
The same production.
Yeah. But this molecule was the same, I think the final. No, it was two iodides, it had,
Was it the same?
there was a ring opening one with,
It was a ring opening, I think it was that.
there,
There was one that could, methanol, right?
yes,
It was the one that created the methanol because that negative charge popped up.
That was the lithium, lithium hydride. We remember this well, I think we do.
It was that one.
Yeah.
Yeah,
Oh,
this
there
one.
we go. So it was that one that I was
This one.
kind of confused on.
So the trick with these is remember that the temperature dictates, is it going through the thermodynamic product
Or the kinetic.
or the kinetic product? And the thermodynamic product means make the most substituted alkene possible. And the kinetic product means make the most stable intermediate possible, make the most stable carbocation possible.
Well, I mean,
So if you protonate this carbon here, then puts a positive charge there, that's not your most, that'll give you. But if you resonate it, then
if you
put
resonate it, then
you
it
get a tertiary carbocation, and that's a better target for the bromide.
I think I just got the arrow pushing a little bit wrong. I think that's all.
And this document is the one that's linked.
So go ahead and do the one that's linked that has this, so it's slightly different, but we'll talk about the specifics of these. It's mostly the same with a little bit.
Okay,
Yeah, you're-
That's just not right.
I think it's actually, might actually be the one that's linked might have actually been your practice test.
I think so. It was the practice. Okay.
But go ahead and do that. Do that again for your review. Turn it in. And then on either Thursday or next Tuesday, I'll give you back your other tests. We'll talk about them in more detail.
No big deal.
Actually, you know, with it being different enough and you already have the practice test anyway, I'll just give you your test right. Cause then I don't have to carry it around.
Yeah, there you go. Yeah, we pretty much on the site. We did it on there.
As usual, good work all around.
Thank you. Oh, of course I forgot.
And actually, I will say everybody got within 2 points of their score on the midterm.
Yeah.
That, which is a small sample size, but that's still, okay, you did just as well in the finals you did on the midterm.
Oh, actually, the mechanism right for that.